This is Professor Needing. I'm going to start the review for examination number 2 we have upcoming. I'm going to break this into 3 parts. First part I'm going to do is chapter 3, and then I'm going to do the P1 section, probability, and then we'll end it with chapter 4. So first, we're supposed to identify either whether we have a parameter. Remember, when a parameter talks about a large group of people, the whole group of people, or we have a statistic, a small group. We're supposed to give the correct notation. Correlation. So the first word I see here is correlation. Correlation means that we have a scatter plot because we have 2 pieces of quantitative data. So the question is, do we have a correlation between a large group, the entire group, or just a statistical group? And it says we have heights and spans, all players on the Cleveland Cavaliers basketball team using data from all players. So we have the word all players and of all Cavaliers. So we have a parameter. That parameter is going to be a row value. I got a really bad row symbol right there, so I wrote the word row. If you don't like to make the symbol, which I don't really, then just write RHO, row. The proportion. So I know, first of all, I have a p-hat or a p-value of students who smoke at LC based on the data from my class. Well, my class is a small subclass of the large class, so mine's p-hat. Correlation, we're back to the same thing going on here. Between the price of textbooks and the number of pages based on only 25 textbooks. Okay, well now it's not a row value, now it's an R value. R is the statistic for a row value from a parameter. So far we have a parameter, we have a statistic, we have another statistic. Average commute time for all employees on a small company based on interviews with all of the employees. Okay, well, all means all, and it's an average, so therefore we have a mu value because it's a all situation. We have average gas prices in Minnesota based on the price of randomly selected people, or randomly selected stations, sorry. Well, then we have a statistic, and the statistic for an average is a mu value. Mu of a statistic is x bar. Proportion, so we're either a p-hat or a p-value of students who enrolled in all LCC colleges in Ohio based on the semester, based on LCC in 2018. So we're using a smaller subset to talk about all community colleges, but it's a smaller subset we're speaking of, so it's a p-hat value. Identify whether each of the following samples is a possible bootstrap. Okay, well, remember, bootstrap sample is drawn from a set of values with replacement. So I go through here and I look, and first of all, I see a 22 right here. I have it x'd off. Well, 22 is not possible because 22 is not inside of the original sample, so it's not possible. I come across these, 24, 19, 24, 20. These are all in the original sample, so therefore it's possible. 21 was not in the original data value, not possible. These are possible. You could have all 20s. You could have all the same number always, as long as it's the same number n for the same value you had, and one of those values is here. Again, same thing, 18, 19, 23s, that's fine. Doesn't have to be a different number, it just has to come from the sample we're talking about. What's wrong with this one here is, well, we're missing a value. Remember, it's always of the same size. This one was not the same size, so it's not possible. Fill in the blank. In October 2012, a survey of 7,786 randomly selected adults living in Germany, 5,840 said they exercised for at least 30 minutes, 3 or more times per week. The sample is, well, the sample is, and I didn't have enough to write everything is, it is 7,786 adults living in Germany. That's the sample. We are measuring the proportion because we're going to talk about the number of people out of that 7,786. And it says the proper notation have to be p-hat because it's a sampling of a value. It's not a parameter, it's a statistic. The best estimate for this population would be, I get 0.75, and I got that by taking 5,840 and dividing it by 7,786. 0.75 would be my p-hat notation of my statistic. Question 4 says, according to the US Census, 71.6% of Americans are age 21 and over. The provided figure shows possible sampling distributions for the proportion sample ages 21 and over from size n equal 50, n equal 125, and n equal 250. Well, what do we know about larger sample sizes? Larger sample sizes give better statistics. Better statistics means closer to the true population parameter. Less number of samplings gives a broader scope, not always as accurate or refined, I guess you would say. So when I look at these three different pictures, this one is very spread out. This one is not so badly spread out, and this one is tighter than all of them. So when I'm looking at the sample size of having the greatest number of n values, the best looking picture or the best one that is centered up in the middle with everything as close or smallest standard error, if you will, would be sample A, 250. When I go to B, well, B is the most spread out. And remember, when I'm talking about my data is spread from here to here versus from here to here. And then in between there, I have the sampling here. Greatest number of n, lesser number of n, least number of n. Sampling distribution shows sampling proportions from n of 35 with 1,000 bootstraps. Okay, this is an important question to talk about. What does one dot on the sampling distribution represent? Well, A1 dot means you took N35, this one right here, you took 35 things and you got an average from it. Actually, this is a proportion. So you got a proportional value right here. That was the average proportion going on for that sampling of 35 things. Estimate the population per from the dot plot. Well, that's in the center, 0.63. Estimate the standard error. Okay, well, I'm going to go to the center. I'm going to say, okay, how far to jump over 1? 0.7, 0.7, 0.7, 0.7. My standard error, 0.07. Use the sampling distribution. How likely is it to have a parameter statistic, or excuse me, a p-value, not a param, of 0.065? Well, if p hat is 0.065, that's right here, and we're looking at having something like that, that's very close to the middle. Because it's very close to the middle, 63, it's reasonably likely. If it were way out here, not very, extremely unlikely way out here, unusual right here. Using the sampling distribution, how likely is 0.45? Okay, so I come down to 0.45 and I come here. 0.45 has dots around it. If it has dots around it, it's unusual, but it might occur occasionally. The further out on the tail, the less likely for it to happen often. The closer to the middle, the more likely for it to happen often. Using this distribution, how likely is it for a 0.98? Okay, well, 0.98 is off the scale. I can't even see it. That doesn't mean it won't happen. It means it's extremely unlikely that it will happen. It says, if sample size n equals 65 had been used instead of n35, so if we had increased the number of n values, now remember what that did on the last page, as we increased n, we brought the values inward. So if we had used 65 instead of 35, which one of these will be true? Well, the sample statistic would have been a better estimate of the population parameter. It would have been a better estimate because the dots that we're seeing under the distribution would have been drawn inward towards the center. Their standard error would have become less. If sample size N65 had been used instead of N35, what of the following would be true? So if I read through these, the sample statistic would have less variability. You have always achieve less variability or less spread of the data when you increase the n value, which therefore increases a better estimate of the population parameter. And it says the statistic would have been a better estimate, meaning the statistic would have been closer to the true center of the population parameter. Number 6. In 2010, the Center for Disease Control Prevention says that 9.4% of children under 18 had asthma. They reported a standard error, not a measurement of error, but a standard error of 0.35%. Assuming that the sampling distribution is symmetric and bell-shaped, find the 95% CI. We take the center of the statistic, 9.4. We plus and minus 2 standard errors, 0.35, we get 8.7 to 10.1. Now, if we were to write this out, we believe that the sampling is between 8.7% and 10.1% for these children who have asthma. Do a little adjustment here, please. A sample of 148 students, sleeping average of 6.85 hours weeknights with a margin of error. Now, a margin of error is different than a standard error. Margin of errors are not times 2, standard errors are times 2. Based on this information, identify the following: plausible or not plausible. Well, the first thing I'm going to do is take my 6.85 right here. I'm going to add and subtract one measurement of error to get a CI of 6.5 to 7.2. This is my first key that I have to do before I can answer these questions. 6.6 hours. Okay, 6.6 is inside of the CI, plausible. 7.5, not inside of the CI, outside of it, not plausible. 8, outside of the CI, not plausible. All I need to do is figure out the CI. Once I know the CI, I can determine plausibility or not plausibility. Number 8. I know this one throws us for a loop sometimes, but let's watch this one. Use the percentiles to report a 95% CI. Okay, a 95% CI means 5% remaining. 5% means 2.5% on each side. 2.5%, 2.5% from the top and from the bottom. So my first CI is 6.322 to 8.082. I do the same thing for a 90, which means 10% divided by 2 is 5%. I find 5% up and I find 5% down. 6.438 to 7.947. 80%, that means 20% divided by 2, which is 10%. 10% up, 10% down. 6.593 to 7.780. I think we have the same kind of simple notation going on. So we have use a percentile to provide a 92% confidence interval. Well, 92 means 8% left over. 8% left over means 4% on each side. 4% on each side indicates 6.1560 to 95.780. Interpret your 92% confidence interval level for the situation. And a lot of us have, questioned, okay, what exactly am I interpreting here? Well, remember, what you're making here is a range, right? So I think the true statement is the one I wrote it for you, and I'm just going to read the one I wrote because I really like it. We are 92% confident, or 92% sure that the true mean, notice that's in big bold, the true mean amount of time for all, you got to use the word all, U.S. adults spent watching the presidential election coverage on election night is between 65.160 and 95.780 minutes. Have to use those pieces of terminology when you're making those descriptions, please. Number 10, in a poll conducted before the Republican president primary in Michigan, 134 of 420 voters were planned to vote for Mitt Romney. Use the appropriate notation. P hat, that's our statistic, is 134 out of 420, which is approximately 0.319. Said 3 decimals right here. Suppose an article describing the poll says that the margin of error is 0.05. Use the information to find this. Okay, well, how do we find a margin of error? We take our statistic, 0.319. We add and subtract the margin of error, 0.045, and we wind up with a value of 0.274 to 0.364. Now, again, we're gonna state what we think we have found in this confidence interval level. We are 95% sure that the true proportion, not the mean this time, the proportion of all Michigan, you got to use the word all, Michigan voters that plan to vote for Romney is between, now don't use this, I'm going to use 27.4% and 36.4%. Okay, let's pick it up. If the proportion of smokers between I think it's supposed to be male and female students. P of M, P of F is 0.05, and the standard error is 0.056. Remember, standard errors get doubled. Find and interpret the confidence interval for 95%. Okay, so here we go. 0.05, that's our statistic, plus or minus 2 times the standard error, 0.056, gives us a confidence interval level between negative 0.062 and 162. Let's make the interpretation. Oh, no, it actually doesn't make for the interpretation time. It says, it does say interpret actually. So I think I typed up, 95% sure that the difference in proportion, because we have to state the word difference and we have to state the word proportion and we have to say the word again, all smokers, between male and female, because we have to make that statement for there, is between negative 6.2% and 16.2%. Okay. Again, don't report the decimal here, report the percentile of the decimal. Then, is it plausible there's no difference? Remember what no difference means. No difference means 0. And the answer is yes, because 0 is between negative 0.062 and 162. So it's plausible that 0 takes place. If 0 wasn't in the CI, then no, it's not plausible for 0 to happen. It says a sample size 46 with a mean of 13.6 is to be used to construct a confidence interval. Okay. For bootstrapped on 1,000. Where will the bootstrap distribution be centered? Well, remember, the bootstrap is around, like up here, the sample of size 46 with a mean of 13.6. It's not the mu that we're dealing with here, it's the 13.6 mean value. That's why we always center up around the sampling on the mean, on the bootstrapping. Number 13, in a recent poll of 1,000 American adults, the number saying exercise is an important part of daily life was 623. Answer the following. Okay, well, first of all, let's analyze some things here. Original sample, 0.623, it's right there. The bootstrap distribution, so you took a sample and you got a proportion, okay? Remember, that's not the original sample, that's the bootstrap. The original sample mean is 0.623. The center of the bootstrap distribution will be around the original sample, because remember, the bootstraps are being taken from this. This is the pretend population for the bootstrap. The size of the bootstrap, 1,000. I can see it right there. Oops, a little low for you, sorry. 1,000 right there. And the standard error. Okay, well, if I look at the standard error is right here, 0.015. It says to estimate, I gotta scoot up some more. It says to estimate the 98% CI. Okay, well, 98% CI. We don't know how to calculate that mathematically, but we do know how to find 98% of 1,000. So what we do is we say, okay, well, if 98% is in the middle, then 2% is on the outside, which means 1% is on this tail, and 1% is on this tail. Okay, 1% on the left, 1% on the right. Well, if we calculate 1% of 1,000, because there's 1,000 dots right there, then that's about 10 dots. So we go this way and we count this way 10 dots, and we go this way and we count 10 dots. We approximate 0.588 and 6.59. Again, that's an approximation. I'm counting dots and I'm looking at the scale and I'm figuring, okay, this is 0.64, this is 0.65, this is 0.66, and where am I going to find that? 0.659. A biologist collects data on a random sample of porcupines. She wants to estimate the correlation between the body mass of the porcupine and the length. Again, Q and Q, quantitative. The bootstrap distribution for the correlation between body mass based on 1,000 is provided. The sample size would be, well, it's the 20 porcupines. N equal 20 for the 20 porcupines. Would it be appropriate to use this bootstrap distribution for 95% CI? Look at this lumpy thing. No, it would not be appropriate. It's not bell-shaped and symmetrical. It's very unsymmetrical. So no, not symmetrical. 15. It says, in a study of these 2,625 U.S. adults, ask whether they agree or disagree on the table and respond to a general. Okay. So a couple things. One, use the information of the table to construct a 95% CI for the difference in proportions who agree, between males and females. Okay, males who agree, 0.307. Females who agree, 0.257. 363 divided by 1412, 372 divided by 1213. Here's my decimals. So the difference between these values, P1 minus P2, is 0.05. Right here. The difference between proportions who agree in males and females. There it is. It also says there's a standard error. Remember, standard errors are always multiplied by 2. Statistic plus or minus 2 times the standard error gives a CI of 0.014 to 0.086. I'm going to go over the true-false real quickly. To select a bootstrap sample, we sample with replacement from the original sample to get a new sample of different. Boom, bad word. False. Always same size. Bootstrap statistic will always give exact. No, they will not give exact. They will give approximately the same. False. We can estimate the standard error when using a standard deviation of bootstrap statistics. Yes, the standard deviation of the bootstrap helps us find the standard error of the sample. Constructing a 95% CI for a parameter based on a sample statistic and a standard error from a bootstrap distribution can only be used when the bootstrap distribution is symmetrical and bell-shaped. We just talked about that right here. We didn't use it because it wasn't symmetrical and bell-shaped. So the answer is yes, we do. As you increase the sample size, n, the statistic calculated is the same. No, it's not the same. It comes in. Remember, more n's makes that statistic get better and better and better. More n's. As you increase the sample size, the width of the confidence interval will decrease. Absolutely. CI will go down. As the level of confidence increases, the width of the confidence calculated will increase. True. It will get broader. If you make the CI larger, you will get more dots. The interval estimate for mu1 minus mu2 using x bar 1 minus x bar 2 is 15 with a margin of error of 2. Remember, a margin of error is times 1 and a standard error is times 2. Is from 11 to 19. False, because 15 plus 2 is 17. 15 minus 2 is 13. Now, if this was a standard error, then it would be true. The 95% CI for proportion is 0.74 to 0.87. The p-value is 0.95. Is it plausible? Absolutely not. It's outside of the CI. Assuming the sampling distribution is symmetrical and bell-shaped with a p-hat of 0.29 and the standard error is 0.4, then the 95% CI is from here to here. Remember, 0.29 is the standard error. You multiply the standard error times 2, and you add and subtract to 0.29, and you get 0.21 and 0.37. To create a 85% CI, sorry, unplugged my microphone accidentally. To create an 85% CI from a bootstrap distribution, we should chop off 7.5% from each tail. True. 7.5 and 7.5 is 15%. 15% and 85% is 100%. If our bootstrap distribution contains 1,000 values or 1,000 bootstrap samples, to create a 90% CI, we should chop off 10 values. Not 10 values, 10% total, which means 5% on each side, and 5% of 1,000 is not 10. An interval estimate is believed to contain the actual values of the parameter. True. As you increase the bootstrap sample, so as n goes up, the width of the confidence interval calculated will increase. That's not true. Remember, as you make more bootstrap samples, you don't, as you increase n, your CI comes in. The 95% confidence means 95% of the intervals constructed will contain the population parameter. That's what we're going for. Remember that little green, that little green tree that we made when we did these, and I ran that tree for you, and how many times do we miss and how many times don't we miss? A random sample of 1,483 adults in the U.S. were asked whether they considered a car a necessity of luxury or a luxury, and we find that we have a 95% CI for the proportion saying that it is a necessity from 83 to 89. Choose the correct interpretation. Okay, well, first of all, remember, we never talk about probability. 95% of all, that's not what we talk about. We're 95% sure, well, that sounds good, that between 83 and, again, it's not talking about all. We have to get something and we'll find down here that we're 95% sure that we need that. We need true proportion. It's got to say true proportion. And it's got to say of all adults in the US. Then it's got to state the statistic 83 to 89%. The most important things are 95% sure, true proportion of all adults. Look for those pieces of parameter. Suppose a 95% CI of a mean score on a fitness exam goes from 67 to 73, based on N30. And a bootstrap distribution contained 5,000 samples for each change described. Okay. State what the CI would most likely result. Okay. So using the data, we find a 99% CI. Okay. Well, we had a 67 to 73, so we're going to increase it. We're going to make this number get lower and make this number get larger. That's the only one that does that. B, using data to find a 90% CI. Okay, well now we're going from a 95 to a 90. So we're going to bring it inward. So we're going to make this go to the right, and we're going to make this go to the left. That's the only number that does that. Letter C, using the original sample size of N45. So what did we do? We took N30 and we increased it to N45. What does that do? It makes it smaller. This is the only one that comes inward. N makes it come inward. Using an original sample size of N16, okay, it's just the opposite, right? So now, because we went from a 30 to a 16, now we're going to balloon that thing outward. We're going to lose accuracy, and we're going to make a larger CI. Using 10,000 bootstrap samples from the same distribution, running more bootstraps doesn't change anything. Still 67 to 73. The only thing that changes things is changing N or changing the actual percentile. I'm going to stop here for chapter 3, and my next one will be for chapter P1.